All right, welcome back to the our third class meeting. The plan for today is to finish up 2-1, start 2-2, and I neglected to write it on the today's plan, but also start into 2-3. So solving general equations, general linear equations. My office hours are posted and available now on Blackboard on the Zoom tab under Zoom links. You can find both the days and times as well as the link for office hours. So office hours just pop in. So these are times that I'll just have this the Zoom meeting associated with this link. Note that it's different than our class meeting, right? Because it applies to all of my students. Our class meetings are all different links. But so you can just go to the link for office hours that's posted on Blackboard in the Zoom links tab. And yeah, just pop in any of these times: Monday, Wednesday, 9 to 10, Tuesday, Thursday, 10:30 to 11. So for half an hour right after class, or Friday, 9 to 11. And of course, I have to set 5 hours each week as my kind of set office hours. But if these hours don't work for you for some reason, reach out, let me know, and we can find a time to meet that does work for you. Our quote of the day today from the Roman lyric poet Horace. And this is a rough translation, but I like this translation. I think it gets at the heart of it. There is a mean in all things, too far to the right or left of which good cannot be found. So that is our quote of the day today from antiquity. Uh, I like to mix it up. Sometimes, ancient Greek or Roman stuff, sometimes more modern ideas. All right, so last time we were working on section 2-1. We were looking at solving equations by the addition or subtraction property. And remember a couple of key ideas. One of the key ideas was the difference between an expression and an equation. An expression is just kind of like a phrase or an idea, and an equation is a claim or a statement of truth. To make sure that that statement of truth doesn't change from line to line, when we do something to one side of the equation, we have to do it to the other side of the equation. And pretty much we can do anything we want to one side of the equation, so long as we also do it to the other side of the equation. I suppose maybe possibly an exception to that will be multiplying by 0. That might change the truth value, but kind of aside from that, really anything else we do, we'll keep that truth value the same going from line to line. And another principle we talked about a little bit was, well, right here I have a pretty complex equation. There's just a lot going on. There are a couple of terms on each side. I don't want to start by trying to subtract 3 times x minus 7 from both sides. That's probably not going to get me very far. Or, adding 4x to both sides. I don't want to start by increasing complexity. I want to start by decreasing complexity. I also noticed that I have some kind of parentheses here. So I have some stuff that can be expanded out. And I think that's where I'm going to start. I'm going to start by expanding things out. And maybe for one step, it's going to look a little bit more complicated because there will be more terms on both sides. But I think we'll see once we expand things out, once we use our distributive property, get all of our terms into the situation where they're pretty simple terms, then we can combine a bunch of like terms together, and hopefully we'll work our way down to something pretty simple. Okay, let's start on the left-hand side. If you don't remember the distributive property, that is A times B plus C equals AB plus AC. That should look pretty familiar. If it doesn't, again, you can always jump back to chapter 1 and review some of that material. But here we get 5x plus 5 times 2 is 10. My minus 4x comes down. And I like to kind of check off things as I'm going along, so just so I make sure I don't miss anything. And then on the other side of the equal sign, I have 3x minus 3 times 7 is minus 21. And here I have to be a little bit careful. How do I handle this minus 3 times x minus 1? Might be tempting to do something like minus 3x, and then 3 times minus 1 is minus 3, so like minus 3. But we've actually made an error with the negative sign if we do that. So let's take this, let's take one more step here and just recognize that minus 3 times something is the same as plus negative 3 times that thing. Breaking it out like this shows us that we have plus and negative 3x, or just a minus 3x. And then plus negative 3 times negative 1 is plus 3. So making sure to distribute that negative along with the 3. Again, if you find that that's an area where you make errors often, and that's an area where a lot of people make errors often, I would recommend maybe taking this one extra step, just rewriting it as plus a negative whatever times the parentheses. But when you get a little more used to it, you can just kind of think of distributing the negative alongside the 3, and it goes a little bit more quickly. Now I see on each side of my equal sign, I have two different types of terms. I have x terms, and I have constant terms. On the left side, I only have one constant term, but I have two x terms. 5x minus 4x is just x, and then plus 10. That plus 10 doesn't have any other like terms to combine with. Moving a little faster now that we've got up to speed a little bit on combined like terms, things like that last time. On the right side, if I combine my x's together, I have 3x minus 3x. They actually go away. They give me a 0x or just a 0. I just don't write that. And then my constant terms, minus 21 plus 3 is minus 18. And now I've gotten myself down to a much simpler looking equation. X plus 10 equals negative 18. It's kind of a messy looking 8. That's a little better. So now I've made some progress, but really what I want is x equals number. And as I mentioned last time, we'll basically call that a solution. Okay, yeah, good question. From Blaze, how do you know when to distribute and when to do the parentheses first? Um, so basically, there's nothing I can do inside the parentheses here. So x plus 2 inside the parentheses, I can't really simplify that at all. So then I move on to distributing. If I had, let's just say as kind of an off to the side, an aside example, if I was dealing with like 5 times x plus 2 minus 2x plus 4, here I would simplify inside the parentheses first. I would say x minus 2x is negative x. Sorry, my allergies are bothering me this morning for some reason. You would think that all of the allergens would be gone with it being this cold, but I don't know what my deal is this morning. But anyway, x minus 2x is negative x, and then 2 plus 4 is plus 6. And now we've got our parentheses, the inside of our parentheses down to where we can't simplify it anymore. That negative x plus 6, that just is what it is. There's no way I can make that simpler. And now I can go ahead and distribute. Yep. Yeah, good question, though. If we had more complicated stuff inside of our parentheses for any of these, for the x plus 2, the x minus 7, or the x minus 1, we would simplify the inside of the parentheses first, get it down to where it's as simple as it can be, but each of these three parentheses happens to be as simple as they can get as it stands now. Okay, so we got x plus 10 equals negative 18. And our goal is to get x equals number. So we have this plus 10 that's kind of stuck onto our x. We got to get rid of it. We do that with a minus 10. So the x plus 10 minus 10 is just x. And if I do that to one side of the equation, better do it to the other side as well. X plus 10 minus 10 on the left is x. Negative 18, be careful with the signs here. Negative 18 minus another 10, which is, I think, maybe what temperature it is outside today. But that's negative 28. Maybe it just feels like my wife and I were just hanging out watching a little bit of YouTube before bed last night, and it recommended this video on like how like legit Eskimos, like Inuit people, build igloos. It was really fascinating actually. There's a lot more engineering behind it, behind this um, architectural form, I guess, from thousands of years ago than you might realize. But but I was like, I wonder why they're recommending this to us. Should I be building an igloo around my house or something? Or um, certainly feels like we're in Alaska today. But yeah, so x equals negative 28, our answer. And as I have mentioned a few times in the past, ideally we'd want to plug this negative 28 back into the original equation all the way back at the beginning, and simplify both sides and check that we get the number the number on each side equaling one another. For time consideration, we're not going to typically do that in class, but that's something that you want to do on an exam, certainly, and on homework as well, especially if you enter the answer and it comes back as wrong. Um, plug it back in, see if you think that's the right answer, or if not, then check your work. Okay, so we will take a few minutes here. We'll take about 3 minutes. Um, I'll let you do this exercise. So work through it. It's going to be pretty similar to, I'll actually leave this one on the screen, pretty similar to the one we just did. And as usual, about a minute and a half in, I'll write out a few notes. And then in about 3 minutes from now, we'll come back and discuss the solution. So take about 3 minutes, work through this exercise, and we will come back and discuss. Okay, it's about 2.5 minutes, but we'll call it now. So again, just like the previous one, we first look for simplification. Can we make each term a little bit simpler, and then can we get ourselves into a position where we can combine a whole bunch of like terms? And that's what we do. First, we distribute in order to break the terms into their kind of like x terms and their constant terms. Kind of in a sense, right now I have like an x minus 1 term, an x plus 3 term, and another x minus 1 term, but those all look a little different, right? I want them to be either x terms or constant terms. And just as a reminder, terms are things that are connected by pluses or minuses. So like I see a minus here, so it's connecting this term to that term. This minus is kind of hidden inside of the parentheses, so it's not, uh, you know, it's not part of something that's splitting up terms. But so I went from 2 terms, one of which was pretty complicated, to 3 terms that are simpler. Or I went from 2 terms, both of which are pretty complicated, to 4 terms that are simpler. But with the simpler terms, I can then combine them together, bringing me all the way down to x minus 5 equals 12. And then again, I have this minus 5 attached to my x. How do I get rid of it? Plus 5 on both sides. X minus 5 plus 5 is x, and 12 plus 5 is 17. And we would then plug back in, check, make sure that comes out correctly. Any questions on this so far? Okay, what about a word problem? So here's a word problem that isn't that difficult, but we do have to be pretty careful about one little detail. So there's not a whole lot of words here. 12 less than x is equal to 17. We want to translate to an equation and solve the equation. So I see pretty clearly is equal to, probably going to represent my equal sign, but sometimes is equal to is just kind of shortened to is, right? 12 less than x is 17 would mean the same thing. So if I see the word is equal to, it's pretty obvious that's an equal sign, but if I see the word is often indicates equals as well, but I see this as my equal sign. If I'm looking to translate to an equation, a lot of times this is like um, a nice starting point to look for. Almost like, if you think of the English language, if somebody is like learning the English language, maybe as a second language or something, or um, probably not as a kid because you kind of pick up things organically a lot earlier than you start to parse things carefully grammatically. Um, but you might say, okay, we usually when we speak, we have subject, verb, object. We're an SVO language. So if I can pluck out the verb, that kind of splits the 2 phrases, at least for simple sentences, right? If I can pull the verb out, then I can say, okay, I got the verb. Now I can look at what's the subject and what's the object from there. And that's kind of what we're doing here. We're pulling out the verb, we're pulling out the equal sign, and then we can look at our 2 expressions, our 2 phrases that are supposedly equal to one another. We can look at those separately. So before is equal to, I have 12 less than x, and after I have 17. Well, 17 is easy. Let's just write that one down. Now 12 less than x. We have to be a little careful here. We might be tempted to just write, well, less than kind of means minus, so we might be tempted to write something like 12 minus x. But think of it this way. If I had $12 less than you do, and you have $20, I don't have it's not 12 minus something, it's 20 minus something, right? It's 20 minus. If I have $12 less than you do, and you have $20, 12 less than 20 is 8. So it'd be like 20 minus 12, where it actually kind of goes this direction. 12 less than x is x minus 12. Now, if it was 12 minus x, then it would be 12 minus x. So 12 less than x means we're taking what x is, whatever that number is, and reducing it by 12. Where 12 minus x means we're taking 12 and we're reducing it by x. So being careful with the order is important here. And it's especially important because we have a minus sign and order does matter with minus, right? There's no commutative property for subtraction. X minus 12 is not the same as 12 minus x. If this were a plus sign and we got the order incorrect, we would still get the right answer at the end, but not with the minus sign. So we have to be a little careful with this. But after we parse out this, we start by looking for the equal sign. That splits our two expressions, our two phrases. The right-hand phrase, super easy, it's just the number 17. The left-hand phrase, a little bit more difficult to figure out, but we got it. We now just have an equation, x minus 12 equals 17. One big idea in math is if I have a certain structure that I know how to work with, I have a certain type of equation or a certain type of problem I know how to solve. If I'm looking at a different problem that seems kind of related to that, we often ask ourselves, can I reduce this new problem to a previously solved problem? And that's what we've done here. We know how to solve this problem. I have x minus something equals number. I just add 12 to both sides. That gets the minus 12 off the left side, leaving me with just x. X minus 12 plus 12, x plus 0 is just x. And on the right side, I have 17 plus 12 is 29. Is it true? So here I can go back and check. Is it true to make the statement 12 less than 29 is 17, or is equal to 17? And yeah, that seems true. If I do 12 less than 29, if I start with 29 and I lose 12, that is 17. So that is a sensible statement, right? If I had got it backwards for some reason, I would have ended up with what, like -5 or something like that. And if I said 12 less than -5 is 17, well, that wouldn't really seem to work. Okay, so let's take a couple minutes and do a quick exercise. So again, maybe let's take about 2 minutes for this, but read through this. Um, you're actually given the equation here as part of the exercise, but read through, see if you can figure out where that equation comes from, and then solve the equation. And actually do the fractions work to simplify your solution as well. So um, we'll take about 2.5 minutes for this and come back and discuss it. Okay, let's look at this one. So where does this equation come from? This is kind of one of the two challenging parts of this problem. Well, we have a bolt that's 7/16 of an inch, and we have to be careful here. We want the bolt to be larger than the hole. The idea is that if we have like a bolt or a screw, it has threads on it, and if we made the hole larger than the bolt, it would just kind of slide in and out and wouldn't actually grab onto anything. But if the bolt is a little bit larger than the hole, when we screw it in, the threads will actually grip and hold on. We obviously want a pilot hole, because if we don't drill a pilot hole and we have something 7/16 of an inch is about a half an inch, it's a pretty big bolt. If I just tried to like, force this bolt into the wood with no pilot hole, number one, it's going to be really hard to do. But if I was able to do it, I'm probably going to split the wood and just destroy whatever it is that I'm trying to screw this into. Uh, so I drill a pilot hole to remove some material to make space basically for the shaft of the bolt, but I do want to leave enough that those threads will grip the material, that the shaft of the bolt will push out, and I'll have enough friction to hold on to keep that lag bolt in place. So that's the idea here. So the bolt is 7/16 of an inch, and the bolt should be 1/8 of an inch larger than the hole. And we're speaking all in terms of diameters here. So D we'll call the diameter of the hole. So what do I have? I have basically that 7/16, the diameter of the bolt to the outside of the threads is 1/8 inch larger than the hole. That's what we're desiring. Or that 7/16 equals 1/8 plus D if D represents the diameter of the hole. Or we can just rearrange some things. Uh, we can switch the two sides of the equation, of course. If A equals B, then B equals A. And I can use commutative property to switch the addition around, and I see I get exactly my equation here. D plus 1/8 equals 7/16. Be a little careful, because if we read this a little quickly, we might read this and think, we might somehow interpret this as something like the hole should be 1/8 inch larger than the bolt, or like D equals 7/16 plus 1/8. Not only does that not really make sense from a building thing standpoint, your bolt's just going to fall right out of the hole. But we see that that also just isn't in line with what is actually said here. So we do have to read carefully and critically for these word problems. Now that we've got the equation, we need to solve it. And it's not a particularly hard equation to solve, but then we have to simplify at the end. So we see we have D plus number equals number. Well, I want just D by itself on one side, so D plus 1/8. I subtract 1/8 from both sides, leave me with just D on the left and 7/16 minus 1/8 on the right. And now I need to remember a couple fraction rules. I want a common denominator. And I see that if I make 1/8 into 2/16, multiplying top and bottom by 2, that does give me a common denominator of 16. And I get 7/16 minus 2/16 just gives me 5/16. So the diameter of the hole should be 5/16 of an inch. So I grab my 5/16 inch drill bit and drill my hole. Any questions on that one?
Yeah, I have a question.
Yeah.
So when you were simplifying that fraction, looking for the common denominator,
Hmm.
obviously it's 16, but you didn't do anything to the 7/16. So, um,
Yeah, good question. Because I see that the 1/8 I can make into 2/16.
mhm.
Um, but the 7/16 is already in terms of 16ths, so it didn't need anything done to it. Now, another situation, um, if I had, 1/2 minus 2/3, well, I can't make the 3 look like a 2 or the 2 look like a 3, right? I can make roughly speaking, the 8 look like a 16 by multiplying by 2. So here my LCD would be 6, actually. So my 1/2 would have to become a 3/6, and my 2/3 would have to become 4/6. In this case, I would need to change both of them because my LCD isn't the same as either one of them. But here, for 16 and 8, my LCD is actually 16, so nothing needs to be done with this guy, but this guy needs to change.
Okay.
Yeah.
Got
Yeah, good question though.
it.
Or another way of looking at it is if you break, say, 8 and 16 down into their prime factorizations, we get 3 versus 4 factors of 2. And we're saying we need 4 factors of 2. The 8 needs to pick up a factor of 2, but the 16 already has 4 factors of 2. It's already happy. The 2 and the 3, if we look at their prime factorizations, they're just 2 and 3. 2 and 3, I think I said 2 as I was trying to write 3, and for whatever reason, I usually write what I'm saying. My LCD in this case is 2 times 3. So the 2 needs to pick up a factor of 3, and the 3 needs to pick up a factor of 2. So they both need to change. Yeah.
Got
Yeah.
it.
Yeah. Good question, though. Yep. Any other questions on the bolt and hole problem? Okay. And then maybe take just a minute and then we'll come back and give the answer. But what's a general method to solve x plus a equals b? If a and b are some constant real numbers and x is the variable we want to solve for, what would the solution look like to this equation in terms of a and b? So x equals something that has a's and b's in it. Yeah, take 30 seconds or a minute, uh, think about it, and we'll come back and discuss. Okay, so my goal, as always, is to isolate x, get the x by itself. It has a plus a on it. I can subtract a from both sides, and x plus a equals b. The solution is going to be x equals b minus a. So the general strategy to solve this is to take whatever is added onto x. If I have an equation looks like this, x plus something equals something, x plus number equals number, to be clear. I subtract off the a, the number that's added onto x. I subtract that off of both sides, so I get x equals b minus a. If a or b are negative numbers, I can have, x equals 3 minus a negative 2. That's perfectly fine. So if I had, x minus 2, let's say, well, I think of that as x plus a negative 2, and then this works. As kind of a side note, you know, we could ask a fairly deep question like, what is mathematics, right? If you had to give a characterization, if you had to give a couple sentence statement where you can say everything that we think of as mathematics fits into the statement, and the statement kind of covers all of mathematics, what might such a statement be? It's an extremely tall order. It's extremely difficult to do, but I think something along the lines of the process of generalization through abstraction. So in other words, we've looked at a bunch of specific examples, well, actually mostly last time, but examples that kind of looked like this, or that maybe boiled down to something like this, kind of an x plus a equals b type of equation. And I noticed that in all of these examples, I kind of applied the same strategy, right? I kind of just added or subtracted whatever was attached to x. X plus 10 equals negative 18. I subtracted 10 for both sides. X minus 5 equals 12. I added 5 to both sides, or I subtracted minus 5 from both sides. x minus 12 equals 17, I subtracted negative 12 from both sides, or just added 12 to both sides. I noticed that I had a similar process that I was doing in each of these specific examples. I might be able to abstract a level out and say, well, for this general type of problem, x plus a equals b, regardless of what a and b are, the strategy to solve such a problem is going to be the same. And here's what the strategy is. In this case, the strategy is simply just write down x equals b minus a. So you might even argue that that is really what characterizes math, this idea of I look at a bunch of particular examples of an area, I see some commonality between them, and I abstract out a level so that I can come up with a framework that solves all problems of that type. Now, I don't have to worry if my numbers are negative 12 and 17, or negative 5 and 12, or 10 and negative 18, or some other numbers. I know that I know how to solve all problems of this type now, all problems that can be made to look like x plus a equals b. And I would argue that's really what math is. Um, it's this process of seeing a bunch of particular examples, kind of looking across those examples and trying to find commonalities between them, abstracting up a level, pulling out those commonalities so that when I go back down to that level, I can actually solve all problems of that type with that same strategy. Right. So I don't think math is so much about knowing things like 2 plus 3 equals 5. I think it's more about that mentality, that way of thinking. Okay, jumping into section 2.2 then, looking at other one-step equations. Here we're looking to solve equations like this one. Instead of number plus a variable equals number, we have something like number times variable equals number. So if I have 3 times r equals some number 9/2, again, I want to get this r by itself, but I have that r multiplied by 3. Remember, if we omit the operation, it's taken to be times multiplication. So 3 times r equals 9/2. How do I get rid of that 3 on the left-hand side? How do I get this 3 off of the r? Well, I have to divide by 3. The 3 is multiplied onto the r, so if I divide by 3, 3 times 1/3, or 3 divided by 3 just gives me 1. 1 times r. 1 times r is just r. So I have a coefficient of my variable is what I call this. When I have number times variable, I call that number the coefficient. 3 times r equals number. I want to get that 3, that coefficient, off of my variable. I divide by that coefficient of 3. I do that on the left. I had better also do it on the right. I have my two scales that are balanced. If I take 2/3 of the stuff off the left, leaving me with just 1/3 of the stuff on the left-hand side, I better only have 1/3 of the stuff on the right-hand side as well. So 3r divided by 3, that's like 3 divided by 3 times r, or just r. And over here I have 9/2 divided by 3. And now I need to simplify a bit. I do have a fraction divided by something. I'm going to make this 3 look like a fraction. I can always make a whole number look like a fraction by putting it over 1. And I know that if I divide by a fraction, that's the same as multiplying by its reciprocal, multiplying by its inverse. Or that's 9/2 times 1/3. Or that would be 9 times 1 over 2 times 3. Remember, when I'm multiplying two fractions together, I multiply the numerators together, I multiply the denominators together, that gives me the new numerator and the new denominator. When I'm adding or subtracting fractions, I have to do this whole least common denominator thing. So two very different feels to those two operations. Addition, subtraction for fractions works very differently than multiplication or division for fractions. I see I have some common factors. This 3 can divide with one of the 3's in the 9, leave me with just the 3 on top. So that's 3 over 2 is what's left over. I think r equals 3 halves is my answer. Let's check that. If I plug this into the original equation, does it work? Is it true that 3 times 3 halves equals 9 halves? I put a little question mark above the equals just to indicate that we are querying this. We're not making this claim yet. We're hoping it's true. And a times b over c equals ab over c. Basically because I can think of that a like a over 1, multiply the a against the b, and then c times 1 is just c. Or so this gives me 3 times 3 is 9 halves. Is that equal to 9 halves? Yes. I see this is the solution. So my solution, r equals 3 halves. What if I have something like this, something that's a little more complicated? 7m plus 3m equals 5. I don't want to just start out, say dividing by 7 or something like that, because I'm not in this form yet. The first thing I want to do is simplify. And I notice on the left-hand side, I have some like terms that can combine together. 7m plus 3m gives me 10m. And the 5 on the right-hand side, we can't get much simpler than just a 5. Now I have number times variable equals number. I have a coefficient on my variable of 10 that's multiplied on. I need to get that off of my variable to isolate my variable to get m equals number. So I do that by dividing by 10. And if I do that on the left, I better do it on the right as well. 10m divided by 10 is just like 10 over 10 times m, or just m. And on the right, I have 5 over 10. 5 divided by 10. Or I can see that 5/10 is 1/2. Again, ideally, I would go and check this, but for time's sake, we won't check. But m equals 1/2 will be our answer. Okay, maybe I'll leave this one up. So we have two exercises here, two similar equations to the one we just did, to the ones we just did, the two we just did. So take a look at these. Take maybe 3 minutes or so for both of them. And jot a couple notes. We'll come back in 3 minutes and discuss. Okay, it's close to 3 minutes. Um, there is a question that just popped up in chat. How are you getting the numerator? Are you just doing the same to the top? Um, I think what might be being asked, you can clarify if I misinterpreted, but I think maybe in the second question, how am I getting the numerator up here? Yeah, and on the right-hand side, we have 4 divided by 6. So we could either write this as 4 divided by sine 6. The same way we might write 4 plus 6 or 4 minus 6. Um, but we can also write that as the fraction 4 divided by 6 this way. So it's just that um, these two notations just mean the same thing. So why did I choose one over the other? Well, fractions are a little more recognizable. And this thing, I think it's called the obelus, if I remember right, um, can sometimes look like a plus, especially if I'm writing quickly and not being super careful. So I tend to opt to write fractions, when that's available. So I think that answers the question that you're asking, but if not, you can clarify. Yeah, so for the first one, again, we have number times variable equals number. So we're in this kind of same structure as we've seen up above, like here, where we divide by the coefficient, or like here, where we divide by the coefficient. So we apply the same solution strategy. 5 times r equals 15/7. We divide both sides by 5. So r equals 15/7 divided by 5. And again, we can think of this divided by 5 as like divided by the fraction 5/1, or times the fraction 1/5, inverting that fraction. So r equals 15/7 times 1/5, or 15 times 1/7 times 5. And then I can divide out some common factors, divide out the 5, leaving me with just 3 times 1/7, 3/7. And for the second one, just like above, well, I have a couple of m terms, a couple of variable terms. I don't want to just start off dividing by 8 or dividing by 2. That's jumping the gun. I need to get these variable terms combined together. I need to get things simplified down first. 8m minus 2m gives me 6m equals 4. And now I do have number times variable equals number. It fits that pattern. I divide through by the 6. I get m equals 4 divided by 6, or 4/6. And here I just gave a little bit more detail on the simplification. I choose to, maybe at first glance, maybe I just don't realize that there's a common factor here. But if I wanted to check, what would I do? I would get a prime factorization for the numerator and denominator. 4 breaks down to 2 times 2 is its prime factorization, 6 to 2 times 3. And I do see indeed there's a common factor of 2 that I can divide out. I divide out one of the factors of 2, leaving me with m equals 2/3. Any questions on either of these two exercises? Okay, so let's jump down to this next one now. Again, this looks like a beast of a problem, right? It looks like a very difficult problem. But if we just take it one step at a time, step by step, we work on simplifying things before adding more complexity, I think it's going to be manageable, right? So we don't want to climb up the complexity mountain and get ourselves something really complicated with, you know, say like trying to divide by 5 or something like that. Now we got fractions everywhere to deal with. We want to simplify out first. So let me start by distributing and combining like terms. So for this bit, I have 5x minus 5. And then minus 2x plus 5, they just come down. That's equal to 4x. And then minus 4 times a half. Well, 4 times a half, what's a half of 4? That's 2. That's minus 2. And then this minus 4 has to distribute to the x, minus 4x. And minus 4 times 1/4 is minus 1. Don't forget to bring that minus sign through as well. Or if you wanted to, you could write it as plus a -4 and then distribute the -4. I have some like terms. 5x minus 2x is 3x. Minus 5 plus 5 actually is 0, so I just have 3x equals. On the right side, I have 4x minus 4x. That gives me 0x, and I have minus 2. Minus 1 is minus 3. All of this just boils down to 3x equals -3, which I'll just write again a little more cleanly. And I recognize this pattern. Number times x equals number. I have a coefficient of 3 in front of the x. I divide both sides by 3. X equals -3 divided by 3. I see pretty clearly that is just -1. X equals -1 is my one and only solution to this problem. Questions on this one? So this one looks really terrible. It actually probably was even easier than, these two, because the simplification at the end was so easy. Just, took a few intermediate steps and, it looked scary, but we saw that a bunch of stuff combined together and made it a lot simpler in the end. Okay, so take a look at this exercise. Again, going to be a similar approach. Take maybe about 90 seconds or so to solve this one, and 90 seconds we'll come back and discuss the solution. Okay, it's so just past 90 seconds. So that was maybe a little much on the writing side. Maybe I should have given you 2 minutes. But again, the strategy is pretty straightforward. We multiply everything out carefully. We get 6x minus 12 plus 3x plus 12 on the left. On the right, 4x minus 4. And then this -4 has to distribute to the x and to the plus 2, minus 4x minus 8. Be careful that you don't end up with a plus 8 there at the end and forget about the negative. On the left, I see the minus 12 and the plus 12 go away. 6x plus 3x gives me 9x. On the right, the 4x and the minus 4x go away, and the minus 4 minus 8 gives me minus 12. So I have 9x equals -12 is what all of this boils down to. Right? Again, very important. I actually haven't done any equation solving steps yet. I didn't, add or subtract or multiply or divide anything from both sides of the equation. This is just expanding out, simplifying, just working with the expressions on one side versus the other, just working with the individual phrases. Just kind of taking one side of my balance scale and sorting things out so that they are arranged a little more nicely, and then doing the same to the other side independently. Now I do an equation solving step, divide both sides by 9. Now I actually do something to both sides of the scale, take some weight off of both sides of the scale. On the left, I get x, and on the right, I get negative 12 over 9. Remember that negative a over b is the same as negative a divided by b is the same as a divided by negative b. These all mean exactly the same thing. So I'm choosing to interpret this as negative the fraction 12/9. And I see there's a common factor of 3 that can divide out, leaving me with x equals negative 4/3. I typically leave fractions as improper fractions. I think most of the time you're working with them, that's the nicer way to leave them. Some faculty are sticklers for always putting it in mixed number form. Personally, I don't think mixed numbers are super helpful unless like you're doing measuring for baking or something like that, or if you're trying to locate something on a number line, there are some situations where they're nicer. But when working with the numbers, it's usually nicer to have them in improper fractions. But we could write our answer either of these ways, negative 4/3 or negative 1 1/3. And again, if you don't quite remember how mixed numbers work or how to swap back and forth between mixed numbers and improper fractions, maybe take a look back at the prerequisite material and brush up on that. So these first couple weeks, in addition to, doing some of this algebra stuff, most folks are going to come across a thing here or there that it's like, wait, I kind of don't remember how to do that, or I vaguely remember doing that, but I don't know if I could do it on my own, but myself. When you come across something like that, jot it down in your notes, make a note to come back to that. And that should be some of your studying for these, first couple of weeks, is reviewing some of that prerequisite material. We all have things that either maybe we kind of missed the first time around in the previous course, or maybe we understood at one point, but kind of forgot. So it's as important, perhaps even more important, to make a note and go back and review that stuff when you come across it, as it is to study the new stuff. Okay, and what is a general method to solve ax equals b? Well, we see that if we have ax equals b, number times x equals number, we divide both sides by the coefficient. X equals b divided by a. The same way that x plus a equals b turned into x equals b minus a, where minus subtraction is the kind of the inverse operation of plus addition. We have a similar thing here. The inverse operation of multiplication is division. Those two are kind of, opposites of one another. They in some sense undo one another. So x equals b over a is our general solution to an equation that looks like a times x equals b. If I see an equation that's in this form, I know its solution is going to look like that. Important here that a is non-zero. Of course, if I had like 0 times x equals 3, what value of x could I plug in there to make that equation work? Well, nothing, right? If I plug in x equals 1,000,000, 0 times 1,000,000 is 0. 0 never equals 3. Any questions so far? Okay, so moving on to section 2.3, looking at what we might call two-step equations. So far, in every equation that we've solved between last time and this time, we've had one equation solving step. Now, we had several simplification steps sometimes, so we did a whole bunch of simplification here, but one equation solving step, right? We had, or here, we had one equation solving step, one step where we did something to both sides of the equation. Or same thing down here, we had one equation solving step to get the solution. Just one equation solving step. So these are one-step problems, not because there's only one thing you need to do. There was often a bunch of simplification and combining like terms and things like that. But in terms of the equation solving steps, in terms of the doing something to both sides of the equation at the same time, there was only one of those steps in anything we've looked at so far. Two-step equations have us apply two equation solving steps in sequence to get the solution. We actually have to apply them in the right order. So we're going to use both of these ideas, the fact that we can subtract a number off of both sides to kind of get the variable kind of a little more by itself. And if I have number times variable equals number, I can divide by the coefficient to get the variable completely by itself. So if I look at an example like this, 3a minus 1 equals 11. This might be straightforward enough you can guess an answer. But again, like we mentioned last time, there are some downsides of the guess and check method. One is sometimes the answer is quite difficult to guess. You're not going to really guess it. And the other downside is if I guess the answer, I haven't really confirmed that that's the only answer. Maybe there's other answers out there. For some problems we'll see in MAT090, there might be two answers. By going through all of the steps, when I get an answer at the end, I know that that's an answer, and I actually know also that it's the only answer. So if I look at 3a minus 1 equals 11, I might be tempted to say divide by 3, the coefficient of a first. But I kind of see when I do that, that's going to, if I divide by 3 on both sides, that's just going to give me a whole bunch of fractions. I'm going to end up with a minus a third equals 11 thirds. That doesn't seem so nice. So I want to chip away at this problem a little bit. I noticed that I have a variable term. I can't isolate my variable itself. I can't get a equals something with just a single equation solving step. It's not going to work here. If I do that divided by 3, it's just going to make a mess. But I want to chip away at it. Instead of isolating a variable, the variable itself, instead of getting a equals something, I can't quite do that. But I can do something that heads in that direction. I can isolate the variable term. I can get this 3a by itself. This 3a has a plus 1 on it. Or, sorry, the 3a has a minus 1 on it. I want a plus 1 on both sides. 3a minus 1 plus 1 gives me 3a. And on the right side, 11 plus 1 gives me 12. I've done one equation solving step here. There's one thing that I did to both sides. I put one more unit of mass on each side of the scale. Right? I've used the addition property of equality. That's an equation solving step. But now I've got myself down to a situation that I recognize. I say, wait, this is number times x equals number. I know how to solve this. 3a equals 12. I divide both sides by 3, and I get on the left a equals, and on the right 12 over 3, or a equals 4. If I plug back in the check, is it true that, maybe I'll do this in a different color. Is it true that 3 times 4 minus 1, is that equal to 11? Or is it true that 12 minus 1 equals 11? And I think we can clearly see that that is true. 12 minus 1 is equal to 11. So yes, this is the one and only solution, a equals 4. So, but note that I had to do two equation solving steps here. First, I used my addition property of equality to add a number to both sides. And then I used my multiplication division property of equality to divide by the coefficient. And I had to do them in the right order. If I divided by the 3 first, I mean, it wouldn't be the end of the world. I could still solve it, but it would be messier to solve. I could do them the other way around, but it's not going to be as clean. I'm going to get lots of fractions everywhere that I'm going to have to work with. So what about something like this? 5x plus 7 equals 4. Again, I notice that I have a variable term, and this 5x is the only place that I see a variable in the entire equation. That's actually going to be pretty important. But this 5x, this variable term, is the only place that I see a variable in the equation. Can I isolate the variable term? Can I get this 5x by itself to get 5x equals number? I can't really get x equals number right away, but if I can get 5x equals number, that seems like an improvement. I have a plus 7 attached to the 5x right now. I can subtract 7 from both sides. 5x plus 7 minus 7 gives me 5x. 4 minus 7 on the right. Or that's 5x equals negative 3. I've done one equation solving step, subtracting 7 from both sides. I haven't gotten my full solution. I haven't got x equals number, but I've gotten closer. I've isolated my variable term. Now I'll work on it isolating the variable itself to get x equals number. I'll do that by dividing by 5 on both sides. 5x divided by 5 is x. Negative 3 divided by 5 is negative 3/5. That was my second equation solving step. So these are two-step problems because we need to apply two equation solving steps alongside all of our, multiplying out, simplifying, combining like terms, all of that stuff. But they're two-step problems because there's two equation solving steps that we need to apply. And then what about something like this one? 3a minus 1 equals 4a. Well, here I actually have my variable in two different places. So far, I've only really moved numbers, right? I've divided by 6, or I've added 5 or something like that. But remember, a variable is just kind of a stand-in. It's just taking the place of a number. Any of the things I can do with numbers, I can do with variables. I can add an a to both sides or divide by an a on both sides, or right, um, I can do the same equation solving steps with variables. I want to end up with something like a equals number. I've got to at least get all of the a's on the same side first, right? I don't want like a equals number plus a or something. Uh, I want all of the a's on one side and all of the numbers on the other side. So I first have got to work towards getting all of my variable terms on the same side, right? I have my variable is in two different places here. I've got to get these variable terms on the same side. And I suppose there's a couple different ways I could do that. I could subtract 4a from both sides. 3a minus 4a is negative a. I could do that. But then I have like negative a minus 1 equals 0. Again, not the end of the world, but it's a bit of a pain. I want to strategize a little bit. I want to look a couple steps ahead and ask myself, what would be the better way to go here so that one or two steps down the road, my life is a little easier? Well, actually, if I subtract 3a, 4a minus 3a, number one, it's not globbed onto the negative 1. And number two, it's a positive coefficient. It's a little easier to deal with. 3a minus 3a, these guys go away on the left, and I'm just left with negative 1. And on the right, actually really nicely, 4a minus 3a is just a. So in the process of combining my variable terms together on one side, I actually happen to get the solution. A equals negative 1. Is it true that 3 times negative 1 minus 1 That's negative 3 minus 1. Is that negative 4? Yes, it is. So we just checked it as well. So this wasn't a proper two-step equation to solve because we kind of got lucky and solved it in one equation. Mainly we got lucky because 4a minus 3a is just exactly a. But if this was like 7a minus 3a, we'd have 4a equals negative 1, and then we have to do another step to get the a by itself. Got a little lucky here. It's a simpler version of this, combining my variable terms together. Okay, let's look at these exercises. I have quite a few of them here. We have 4 exercises. So we will take several minutes to work through these. So we'll probably take, I think, maybe 9 minutes to work through these. And again, uh, keep plugging away at them. Get through as many as you can. So if you're moving a little more slowly, you should be able to get through at least, 1 or 2 in that 9 minutes. If you're pretty well up to speed, you should be able to get through all 4. But we'll take about 9 minutes. And as usual, kind of as, every 30 seconds or a minute or so, write up just a little more in case you're stuck somewhere. That can help you get unstuck. So we will touch base in 9 minutes or so. And as always, if you have questions, pop them in the chat. Okay, let's discuss the solutions. I know I said 9 minutes, it's a little early, but um, these seem to go a little faster than I was expecting. Um, so if you didn't get through all four, that's okay. But I think, um, judging by a couple of the messages I got, I think that, most people have gotten through most of them at this point. Um, so the first one, we note that we have a single variable term. So our goal is to get any of the constant terms that are attached to that variable term onto the other side. So we have a 4a minus 7. We can't isolate the variable itself, a, right away, but we can isolate the variable term. We can make a step towards isolating the variable. So we want this minus 7 off of the 4a term, and we add 7 to both sides to get 4a equals 16. And now we reduce this to an equation we know how to solve. This is now a one-step equation. 4a equals 16. We have a coefficient of 4 on our a. That's multiplied on, so we divide by 4 on both sides. 4a divided by 4 is a. 16 divided by 4 is 4. So a equals 4, our solution. And pretty similarly with the next one, solving 14x plus 1 equals 8. Again, we note that we have a single variable term. The variable x only comes up one place in this whole equation. So I want to isolate that variable term. I do that by subtracting 1 from both sides to get that plus 1 off of the 14x. Subtracting 1 on both sides gives me 14x on the left and 8 minus 1, or 7, on the right. And now again, I have number times x equals number. 14 times x equals 7. My coefficient of x is 14. I want to isolate the variable itself. I divide by the coefficient of 14 on both sides. So on the left, that gives me just x. 14 times x divided by 14. The 14s divide out. And on the right side, 7 divided by 14. And 7 over 14, of course, reduces to 1/2. So x equals 1/2, or 0.5, something like that. And I did throw in a little check over here as well, so we can check our work. The next two problems are a little different in that they have more than one variable term. Now note that each side, each expression individually, cannot be simplified any further. 7a minus 1, it's not like I have 7a minus 1 plus 8a equals 3 or something where I can combine some a terms. 7a minus 1 on the left side of the equals is as simple as it can get. 8a on the right side of the equals is as simple as it can get. But I have two variable terms. I want to isolate the variable term. I want to get the variable term on one side of the equals and all of the other just numbers on the other side. So I'll choose to subtract the 7a to get this 7a away from this constant term, get it away from this minus 1 if I could select it. There we go. So I subtract 7a from both sides and I get -1 is what's left over on the left. 8a minus 7a is just 1a, or just a, on the right. So nicely enough, things happen to work out so that I just get a equals -1. And I made a note over here that if I went the other way, in other words, if I had chosen the 8a to subtract off of both sides, it's not like it's irrecoverable or something, but it's just a bit more of a pain. Remember, my goal is to get the a term, number times a, on one side of the equation, and all of the other constants, the constant terms, on the other side. Well, by subtracting 8a, I kind of put the a's on the side with the constant term on it. So 7a minus 8a is -a, minus 1 just kind of comes down, and 8a minus 8a is 0. Now I have one variable term. I have to isolate it by adding 1 to both sides to get that constant term off of it. So I have -a equals 1. And now I have a coefficient, -a equals -1 times a. I have a coefficient of -1 that I have to divide by. So a is 1 over -1, or just -1. I still got the answer, but I had to do actually 3 equation solving steps and deal with a negative. where it's just a little easier to make a mistake when dealing with negative numbers. Right, so it was just more work to do it this way. I want to strategize. I want to look a step or two out and say, where do I want to be a couple of steps from now? Which direction should I move? Should I subtract the 7a and put the a's on the right side? Or should I subtract 8a and put the a's on the left side? In this case, it makes more sense to get the a's on the right side because there's no constant term on the right side. That's really the big factor here. And similarly with this last exercise, 15x plus 7 equals 16x. For the same reason, I choose to subtract 15x from both sides rather than going the other way and subtracting 16x. That leaves me with 7 equals x. Give me 1 second here. Sorry, I just had to sneeze and didn't want to blow your eardrums out sneezing into the microphone. Yeah, so any questions on any of these four? I know there were a couple of questions in chat that I think I've answered already. Any other questions? Okay. Let's move on then. I think we'll actually skip this one. We'll jump over that one. But let's move to this next one. Solve 3a minus 1 equals 10a. Again, I have kind of a setup like these ones, where I've got two variable terms. My goal is to end up with variable equals number. I need to get these two variable terms together, right? And to be clear, these are two variable terms on opposite sides of the equal sign. If they were on the same side, I would just combine them as like terms. But they're on opposite sides of the equal sign. So I need to do an equation solving step to get my variable terms together in the first place. If I were to subtract 10a, that puts the variable terms on the same side as the constant term. That means I have to kind of untangle everything later on. I'm going to go the other way. I'm going to subtract 3a from both sides. On the left, 3a minus 3a is 0, minus 1 is just negative 1. And on the right, 10a minus 3a is 7a. So I have 7a equals negative 1. And now I have successfully isolated my variable term, right? Now there is only one variable term. This variable a only shows up in one place in my equation. I can do another equation solving step. I have number times a equals number. I can divide by that coefficient of 7. Or I have negative 1/7 equals a, or I can flip that around and write it as a equals negative 1/7. Any questions so far? So similarly down here, I have two variable terms. I see my variable x popping up in two different places on either side of the equal sign. So it's not, again, it's not like they're on the same side like some of these ones up here where we just combine like terms. They're really on different sides of the equals. So I've got to isolate my variable terms first. I got to put my variable terms on the same side of the equal sign so I can combine them together into one single variable term that I can then work on isolating. And I want to put them on the right side because I see that there is no constant bit on the right side, but there is a constant bit on the left side. If I can kill two birds with one stone, if I can do two things in one step, that's great. By putting the 5x on the right-hand side, I not only am able to combine it with the 12x, but I also move it away from that constant term of the +7. So I want to move the 5x to the other side instead of moving the 12x to where it would be still coupled in with the plus 7. 5x minus 5x is 0, plus 7 is just 7. 12x minus 5x is 7x. And now I need one more equation solving step. I have number times x equals number. I've isolated the variable term. I only see the variable coming up one place in my equation. I now need to divide by the coefficient of the variable. On the right, 7x over 7 is just x. On the left, 7 over 7 is 1. X equals 1 is my solution. Okay, and I think the last thing we will do today is to run through these two exercises. We have about 7 minutes total, so let's take about 3 to 4 minutes to work on them and then come back and wrap up. So take about 3 to 4 minutes, work on these two exercises, and then we'll chat about them. And that'll be it for today. Okay, let's chat about the solutions to these two exercises, and that'll wrap us up for today. So the first one solves 7a minus 1 equals 15a. Again, we note that there are two variable terms. There's nothing to simplify. There are two variable terms on one on each side of the equation. We see the a popping up twice in the equation, once on each side. And we have this constant term that's attached to the 7a. I need to move one of the variable terms, one of the terms with a, to the other side of the equation so I can combine them together. I might as well move the one that's attached to the constant term off of the constant term. So I'll subtract 7a from both sides, giving me 15a minus 7a on the right. 8a on the right, and just 7a minus 7a is 0, minus 1, just a negative 1 on the left. So I have negative 1 equals 8a. And I note that I now just have one variable term across the entire equation. So I have number times a equals number. And hey, I recognize that structure. I divide by the coefficient of a. I divide by 8, giving me a equals negative 1/8. And I can pop that into the original equation all the way up here, do a bit of arithmetic, and verify that, yes, this is a solution. So I found the one and only solution and check that it's correct. And similarly on the next exercise, solve 5x plus 7 equals 16x. Just like before, we're going to move the 5x so that we kill two birds with one stone. We move the variable terms together, and we also move that variable term off of the constant term. Subtract 5x from both sides gives me 7 equals 11x. And then again, I recognize this pattern, number times x equals number. I divide by the coefficient of x, divide by 11 on both sides to get x equals 7/11. And that's my answer. Just a little side note, when I can answer exactly like this, I always should. Whether that's on pen and paper in maybe a different course, a different, class, a different course, a different section, or whether it's in WebAssign, if 7/11 is the answer, that's what you should enter. You shouldn't enter some decimal approximation unless it specifically asks you to. Things like -1/8, that decimal expansion ends. So would that be negative 0.125? You probably can answer either way, but for WebAssign purposes, look at the problem and see how it asks you to answer. If it says answer as an integer or decimal, move it to decimal form. If it says enter your answer as an integer or a fraction, then enter it as a fraction. And again, if you have questions about moving back and forth between, say, decimals and fractions, either pop in office hours or look at some of the prereq material. All right, so that wraps us up for today. Remember, we have office hours today at 10:30, so take a couple minutes if you have any questions. Come on back. I'll be here 10:30 to 11 at the different link posted on the Blackboard site. So it's not our normal class link, it's a different meeting. And yeah, when we come back on Thursday, we'll continue with section 2.3, moving on to what if we have a constant term and a variable term on both sides of the equation. So two variable terms and two constant terms. How do we handle that? That's the goal for next time. I will see you then. Have a good one.